Welcome back! The component to be discussed in the upcoming 3 videos are related to the PV modules as introduced in the second part of the Solar Energy MOOC. These are the components which convert the solar irradiance into electrical power. The learning objective of this video lecture are to understand the principle of how solar cells are or can be interconnected in photovoltaic modules. And how are interconnections in PV modules realized if we consider different PV technologies like PV modules based on crystalline silicon PV wafers or PV modules based on thin film solar cells. A wafer-based device is usually referred to as a solar cell. A solar module is a larger device in which many solar cells are connected. If you look at the level of a PV system, we can have several modules connected, and this is what we call an array. The dominant PV technologies is based on the crystalline silicon wafers. However, a small fraction of the PV market is based on thin film technologies like cadmium telluride, CIGS, and thin film silicon PV modules. As discussed in the second part of this solar MOOC, are the thin film cells usually directly processed on the glass of the solar modules. The typical dimensions of a single solar cell is usually a strip with a width of 1.5 to 1 centimeter and a length of half to 1.5 meters depending on the width of the PV modules themselves. The individual cells are monolithically interconnected, as will be discussed later. The dimensions of crystalline silicon wafer-based solar cells in industry have been increasing rapidly during the last years due to advancements in ingot manufacturing. A few years ago, 6 inch by 6 inch or 15.5 by 15.5 centimeters were the common wafer sizes used. Currently, wafer size of 21 centimeters by 21 centimeters are becoming the mainstream size. A solar module consists of many solar cells interconnected in a circuit. As of today, the most frequently used design has 60 to 72 individual cells with a total dimension of 1 by 1.6 to 2 meters. In PV system, these modules will again be interconnected to form an array. In order to connect individual solar cells in a module, the bus bars at the front side will be connected to the back contact of the neighboring cell. This process is called contact tabbing. Here you see a cross-sectional view of a few solar cells connected in series. Such a series connection is called a string. There are other ways to interconnect solar cells, such as in the second part of this MOOC discussed metal wrap-through technology. Here the front contacts are wrapped through the cell with a so-called via, such that both the positive and negative terminals are located at the backside of the cell. The cells can now be placed much closer to each other since contact tabbing is omitted. A more advanced way to place all the contacts at the backside of the solar cell is found in the earlier discussed interdigitated back-contacted technology. Both the electrons and holes will be collected at the backside of the cell by alternating placing p and n layers that serve as selective contacts. In this slide, you see a cross-sectional view of a few solar cells connected in series. Every solar cell has its back contact connected with the front contact of its neighboring cell. For series connected cells, the voltages add up, whereas the current does not add up. The current flowing through the solar cell is determined by the photocurrent in each solar cell. It means that the total current in the string of solar cells is equal to the current generated by one single solar cell or the cell generating the lowest current. Let's look at the JV curve of solar cells connected in series. Here you see the IV curve of a single solar cell. If we connect two solar cells in series, it means that we can add up the voltages. However, the current remains the same in series connection. The resulting open circuit voltage is 2 times that of a single cell. If we connect 3 solar cells in series, the open circuit voltage becomes 3 times as large, whereas the current is that of one single solar cell. A second way of connecting the solar cell is in parallel. Parallel connection means that the voltage is the same over all solar cells, however, the currents of the solar cell add up. If we have 2 solar cells connected in parallel, the current increases 2 times, whereas the voltage remains the same. If we have 3 cells in parallel, the current becomes 3 times as large, while the voltage is the same as for a single cell. This means that if we consider a module, you can partly tune the voltage and the current output by the arrangements of the connections of the solar cells. Now we look at how we make a solar module out of an ensemble of solar cells. Here we see a solar panel that contains 36 solar cells connected in series. If a single junction solar cell would have a short circuit current of 8.5 amps and an open circuit voltage of 0.6 volt, it means that the current output of the module is equal to that of a single solar cell, which is 8.5 amps. The open circuit voltage would be 36 times that of a single junction solar cell, which equals 21.6 volt. If you would rearrange the interconnection of this module, we can get a different current and voltage output. If we connect 2 strings of 18 series connected solar cells in parallel, we would get a short circuit current of 2 times that of a single solar cell, which is 17 amps. The open circuit voltage would be 80 times that of a single solar cell, which is 10.8 volts. In thin film technology, producing cells and modules cannot be separated from each other. To fabricate a thin film module, a transparent front contact, a stack of photoactive layers and a back contact are deposited onto each other. In industrial production, the glass plates onto which these layers are deposited can be very large, up to 2.5 by 2.5 square meters. Such a stack of layers basically forms one very large solar cell that will produce a very high current. Since all the current would have to be transported across the front and back contacts, which are very thin, a relatively large fraction of the power would be lost due to resistive losses. Therefore, the module is produced such that it consists of many very narrow cells of about 0.5 to 1 centimeters width, depending on the PV technology, as can be seen in this figure. The length of these narrow cells is equal to the module length. The cells are connected in series across the width. On the very left and right of the module, metallic bus bars will be present to collect the current and conduct it to the bottom of the module, where they are connected with external cables. The series connection of the thin film module is established with laser scribing. Let's go through this process. In general, a total of 3 laser scribes are required to separate 2 cells from each other. To illustrate these laser scribing steps, we will look at this thin film cell deposited in a superstrate configuration. On top of a glass superstrate, the transparent front electrode is deposited. Then the first laser scribe is performed, called P1. The wavelength of the laser is such that it is transmitted through the glass and absorbed by the front contact. The P1 laser scribing step evaporates the material and leaves a gap in the front contact. Then the photoactive layers are deposited on top of the front contact, creating a thin film and filling the gap left by the first laser scribe. After deposition of the absorber layer, the second laser scribe, called P2, is performed. The wavelength of the laser has to be chosen such that it is not absorbed by the glass and transparent front contact, but in the absorber layer. For example, in the case of amorphous silicon absorber layer, green laser lights can be used. The P2 laser scribe leaves a gap in the absorber layer. This gap is filled with the deposition of the final layer, which is the metallic back contact. Then the third laser scribe, called P3, is performed. The wavelength of this laser scribe has to be chosen such that it is transmitted through all of the preceding layers and is only absorbed by the back contact. It may therefore be, for instance, infrared light. The final laser scribe evaporates the metal and creates a gap in the back contacts. So how exactly do these laser scribes create a series connection? The P1 laser scribe interrupts the front electrode and is filled with the absorber material. The absorber material is orders of magnitude less conductive than the front electrode, and the width of the laser scribe is an order of magnitude larger than the thickness of the absorber material in the growth direction. Therefore, the absorber material forms a barrier against lateral charge carrier movement. Similarly, the P3 scribe forms an insulating gap in the metallic back contact. The P2 scribe, however, that is also filled with metal, forms a highly conductive connection between the front and the back contacts. If we zoom out, we can see how the current flows through the P2 scribe and connects the individual cells in series. The area in which the laser scribes take place is called the interconnection width. The cell width is defined by the P3 and the P1 scribes. Now we look at how the voltages and current of a solar module is determined by an ensemble of thin film solar cells. Here we see a solar panel that contains 150 thin film solar cells connected in series. If a single junction solar cell would have a short circuit current of 3.8 amperes and an open circuit voltage of 1 volt, it means that the current output of the module is equal to that of a single solar cell, which is 3.8 amperes. The open circuit voltage would be 150 times that of a single junction cell, which is equal to 150 volts. If we would rearrange the interconnection of this module, we can get a different current and voltage output. If we connect, for instance, two strings of 275 series connected solar cells in parallel, we would get a short circuit current of 2 times that of a single solar cell, which is 7.6 amperes. The open circuit voltage would be 70 times that of a single solar cell, which is 75 volts. Reducing the sensitivity to hotspots, some modules reduce the current per cell by, in this example, cutting them in half using a laser scribe. In this example, the single junction solar cell would have a short circuit current of 1.9 amps and an open circuit voltage of 1 volt. The two strings of 150 volts are connected in parallel, resulting again in a module short circuit current of 3.8 amperes and an open circuit voltage of 150 volts. In summary, we discussed how the realization of interconnection of thin film PV modules is very different from the interconnection of wafer-based crystalline silicon PV modules. The production of crystalline silicon modules consists of 2 distinct steps: the production of cells and connecting several cells into a module. For thin film modules, laser scribes are used to create a series of small cells for what is effectively one very large solar cell. The output voltage and current is determined by the amount of cells series connected in a string and the number of strings connected in parallel. In the next video we will discuss why we need bypass diodes in PV modules and how shading of PV modules impacts its output. So see you in the next video lecture.